Yeah, okay. So I'll just tell you the agenda for today. Today we hope to wrap up both heaps as well as binary search trees. And so essentially what we intend to cover in today's class is basically in the first half, we intend to look at the code for the implementation, right? We discussed all the entire implementation logic of BSTs as well as heaps, right? So today we intend to look at the code for the implementation, and then we will, after that, we will continue with the approach that we were taking since or from the day before yesterday, which is basically looking at applications, looking at patterns of questions which warrant usage of a certain data structure, and we will also look at a couple of more DS design questions which are specific to BSTs and heaps. So far, whatever data structure design we have done with respect to hash tables, right? So today we intend to look at design questions which involve BSTs and heaps also, apart from other data structures that we have already covered. And of course, we intend to look at some more applications of BSTs and heaps. So that's the agenda for today. It might be a long class because I intend to cover and finish off everything by today. If not, then we will have to have another class tomorrow, but we will see how it goes. Okay, sounds good to everyone. Is everyone good to start? Can I have a set of acknowledgements just to know that you guys are there and we are good to start? Right? Okay. So let's quickly start then. We will look at the implementation for each of the three BSTs and heaps today. So if you remember, whether you remember or not, let's see the algorithms. Let me just open up my editor. So the screen is visible to everyone, right? The editor. No issues with respect to that. I will just clear up some of the tabs which are specific to Oracle. So we will basically be looking at implementation of binary search trees first, and followed by that we will look at implementation of heaps. Let me just go ahead and save this file somewhere. Let me just put it in the documents for now. So let's assume that you have a tree node. So let's assume that you have this struct tree node star, and this basic struct tree node, this is a node, and this basically contains three things. It will contain the value, it will contain the pointers to the left and the right, right? So let's assume we already have something like this in place, and we intend to start from here. So this is, I'm just setting things up. So let's say we have a tree node star tree which is null to begin with. Okay, and now we will basically write all the operations for insert, delete, and search. Okay, so let's begin. Let's begin with search. So So search, I'm just assuming it will return a boolean, which is okay. And now let's take the root of the tree as the as one of the arguments, and the value that we want to search for as the another argument. Okay. So what is the algorithm? I compare the current value with the value. So if the current value, let's assume that everything less equals is going to the left half and everything greater is going to the right half. Okay. So if this is, so three things we will do. This is very similar to binary search. So if it is equals to the value, then I can return true. If it is strictly less than the value, then what I will do is I can call search again with root of left and the value, right? Otherwise, I can call search again with root of right and the value, correct? And if I encounter a null in the process, I will basically return false, correct? So this will basically keep, I will keep reducing my search space by one branch of the subtree, right? In every iteration or in at every step. And eventually, if I reach the root, if I reach the leaf, then basically I am done, and I have not been able to find the element. So I will return false. Otherwise, I will keep doing, and as soon as I find the element, I will return true from there, right? So everyone understands the search algorithm?
Yeah. Sir, one small doubt.
Yeah.
In line number 15, shouldn't
Okay.
the operator be other way around? I mean, val less than root dot val.
Wait, you're saying this? Yeah, you're right. Okay. Is this fine, everyone? Is there anyone who is having issues with this? This is just followed up from the algorithm that we discussed yesterday. So if you don't understand this, let me know. I can start the whiteboard and maybe try and explain you the algorithm again. Okay, so I will take it as a yes then, if there is no issue. Let's do insert then. So insert will return the root. So insert, I will just write the prototype, what the function is doing. So this function is checking for the occurrence of an element and returns true if found, false otherwise. Okay. Let's talk about the next algorithm, which is insert. So inserts an element in the tree, and this will return the root of the tree. Let's say we are doing that. You could actually uh, choose not to return anything also. So you could do that as well. Let's do that, and we will see if we can. So let's say we are calling insert on, and this is the value that we want to insert. First, what we will do, we will basically keep going down till we find the place where we insert. So the logic is that we always insert at the leaf, right? So we will just keep going down, and that basically the logic is that, let's say everything less than the value, less equals, I am keeping in the left subtree. So if this element that is being inserted is in the left subtree, is less equals the current element, then I will call insert with on the left subtree. Otherwise, I will call insert on the right subtree. When will this stop? When I reach the leaf, right? So if I reach the leaf, this is how I reach the leaf. Yeah, I mean, you can go ahead with any particular implementation. Like it is not very important. You could go right as well. We have just defined it in that way. Yeah. Okay. So now this is the problem. Now, once we've reached the root, um, we have to basically malloc, right? So see, there are two ways of doing this. Uh, One way is you could return the newly created node. So let's say your definition is, you will get to know what I'm trying to say. So let's say your definition is that you want to return the root. So if you want to return the root, then this is the prototype. And what you can do then is that you will create a new pointer here. Let's go. And then you will assign the value to this left and right pointers to be null, and you can return this. So then what happens is basically that I could do this, and this will work. Why will this work? So just think about the recursive definition. What have I said? I have said that once I will insert an element, I will return the root. So what if the tree is empty? If the tree is empty, then you will simply insert an element, create a new element, and return the root. The root is the newly created element, right? Otherwise, if the tree is not empty, or if the root is not empty, then I will insert appropriately wherever I have to insert. And this call will give me the root of the left subtree, right? By the recursive definition. So I will assign it to root left, and this part will give me the root of the right subtree. So by definition, that is how we have written this function. So I will assign that to root right. And then, because to make this function consistent with the definition, I will return the root. So what I'm trying to say is that I am writing a recursive function here, right? And we discussed like extensively during recursion that you could just write recursive function just at level 1 through just understanding of the definition. So the mission statement, right? Whatever mission statement you have defined, if you are consistent with that mission statement in the during the recursive step as well as during the base case, then you will always be good. You don't really have to think about how the recursion is unfolding. So I have just done that. And if you, what have I done? I have said that what is the base case? The base case is when the tree is empty. So when the tree is empty, then I can create a new node and return the head of the new node. That is basically my tree for now, right? And if the tree is not empty, then I will insert in the appropriate half. And once I insert, according to the mission statement, I know that I am returning the root of that tree. So I will assign it, and then I will return the root. So I am just making sure that this function's definition is consistent with the mission statement, and everything else will work. Do you understand what I'm trying to say? I'm not trying to explain you the function as to how the recursion is unfolding. I am just trying to tell you how I wrote this definition in the first place. So I just defined a mission statement, and I very religiously abided by it. That's it. I have not done anything else. When I wrote this definition, honestly, there is nothing else going in my mind other than just the definition or the mission statement. I just wrote the definition of the function keeping that mission statement in mind. And I will show you that this actually, when you unfold the recursion, this will work. This will work because you are consistent with the mission statement that you have defined. So this is one of the like pro tips of recursion. If you really want to master recursion, you should be able to do this. When you write recursive functions, don't go beyond level 1 when you are writing it. Define a clear mission statement, just abide by the mission statement when you are implementing the function. Everything else will take care of itself. People generally don't do that. What people do is they have the entire recursion unfolding in their mind when they're writing the definition, or when they are implementing the function. And if you go by that route, then you will end up in all sorts of troubles, because you will have to take care of cases, everything. And so that's what the point that I'm trying to drive home through this. I have tried to tell this to you during the recursion lectures as well. Do you follow this? Do you follow not the definition, but what I'm trying to say, the idea, like how you create recursive functions on your own? See, if someone gives you a recursive function, you will be able to draw the recursion tree and understand and convince the person that yes, this works. That is fine, that I know. You will be able to do it, but that's not the point. The point is you should be able to write recursive functions on your own, and that is where this comes in handy. One second. People are interested in joining. Okay. So this is then the insert function. This insert function is clear, both how I wrote it as well as how. Do you want me to do a dry run of this, like through an example? Okay. What about others? So tell me then, what if I had no return value here? How will you modify the definition of this function if you had a void here? Let's say I intended not to return anything. How would you change this function to accommodate that? Let's say by definition, I was just saying that I will just insert that element and I will not return anything. Then what would you have done? Double pointer to what? To the root. Right? So if we are not inserting, then we will have to return implicitly, right? So there are two ways you can return from any recursive function. I had told this before as well. If you don't want to have an explicit return type here, then you could return by key through an argument in the function, right? So if you want to do that, then probably you will have to keep an argument here, which will typically be a pointer to the element that you are returning. So what are you returning? You are returning a pointer to the root, right? So you have to keep a pointer to that. So what is that? That is a double pointer to the root, right? Do you understand this? So then basically you will have to keep a double pointer here. So I give this as a homework. Try it. Try to modify the definition by keeping a void here. And let me know tomorrow if you are able to code this through a void. Okay. Why is the class so silent today? Are you guys feeling sleepy? Do you have a lot of work overload, academic load? What is the issue? So because you are here, you are spending some time here. So please, like, it's your moral responsibility for yourself. You should try to focus. Okay, if because you are spending a lot of, like, 3 hours of your 24 hours, right, which is 1/8 of your time on this in the class. So if you are doing that, then I mean, try to focus. Otherwise it's okay, you can watch the recorded lecture, you can do whatever you want. So both it's like, it's your call, everything works out, it's nothing like that. The only thing is, if you are dedicating time towards something, just do it wholeheartedly. That's the only thing. Otherwise it's okay, you have other ways of resolving the same issue. Let's do the next part, which is the tricky part, which is the delete. Correct, Karan? We will do the dry run of insert after the class, okay? Because you are the only person who want it, so let's do it after the class. Yeah, let's do the delete. So what we will do is deletes the element from the tree and returns the root of the tree. So let's do this. So if I am doing a, so I have a tree node, I will take the root and a value which I want to delete. Now first things first, what I will do is, there are a lot of ways you could do this. First things first is find this element in the tree, right? This is the first thing that I will do. So how will I find it? I could use the search function itself to find it. So let's do that. Search tree and val, right? So I just found it. I am just looking it up. If it is not found, then I can just return. So if it is not found, then let's just return from here. Otherwise, now it is found. So let's actually modify this to return the node. Okay, you could I'm just modifying the function to return the node if found, null otherwise. Okay, so if it is true, then I will return the pointer to the root. If it is greater, then I will search here and return. Otherwise, I will return here. Here I will return a null. So I've just changed the definition, made it changed it slightly to return the node, which if it is found, and null otherwise. So I will basically keep going in the right appropriate subtree till I find the root. As soon as I find the root, as soon as I find that value, I will return that value, and then I will keep returning recursively till the root, right? And if I reach the leaf node, then I will return null, which again keeps going up. So if that is the case, then so this is the element, and if it is null, then I could simply return from here. Otherwise, now I have this element, right? So how do I, so we remember we had three cases here, right? What were the three cases? Can you tell me?
Sir, the deleting leaf itself, and the node with one child, the node with two children.
Node with two children, right?
Yes.
So we have to just take care of those cases. So let's take care of the first case. What is that? That is if it is a leaf node. So how do I know it is a leaf node? I can check if it's left and right both are null. So this will give me, if both of them are null, then it's a leaf node, right? So then what I could do is I could free this. So now I will free this node. I'm autocorrect. So I mallocked using new, right? If you see, so I will free using delete. So I could just do a delete of ELT. So if left is not found, you're saying if left is null. So if left, see, this is and, right? So if this is true, then it will go on to the next element. If this is false, then it will skip the second check, right? So what I'm checking is if both of them are null. So if this part is null, then it will go ahead and do the second check also, because it's an and. Yeah. So now I can just delete this element, and I will need to, so what can I do now? So let's basically, what we can do, what can I do here? I have to make the parent null, right? So how do I do that? Through this, it is actually not possible. We will have to write a recursive function for that. So let's write a recursive function for that. What we will do is, let's do a delete helper. So which has the node that I have to delete. Okay. So now I have the node that I have to delete. And from here, I will basically but I cannot delete here. Yeah, how do I take care of this? Do you understand the problem here? I have to return null. I have to make the parent of this node null, right? So how can I get around this? Any ideas? Root equals null. What do you mean by root equals null? Tell me, how do you take care of this? Any ideas around this? Do you get the question? No, I have to make the parent of ELT null, right? And even in the other cases, in the second and the third case, so case 2 was if left if one child, right? So even in this case, I have to return after deleting the subtree, right, to the parent, or I have to make the parent point to the subtree of this child, whichever child is not null. So my question to you is, how do I do that? because I from this node I cannot go to the parent definitely. Where will you stop before reaching element? In the insert, right? I mean in the searching, right? Yeah. So one like very cheap or very like hacky way of doing it is that you could find the parent of this here itself. You could modify. So there are two ways at least you could do it. You could modify the search to return the parent, but that is definitely like that is not what search should be returning, right? The search should be returning the element which you are looking for and not the parent of that element. So we will not modify the search, but instead once I have searched for it, what I will do is I will basically find the parent of this. So how do I find the parent of this? I could simply keep following the same algorithm. So let's write a helper for that. There are better ways you could do it. I want ideas around that from you. But let's say we go ahead and we find the parent of the element. So you want to find the parent of this element, and the root of the tree is this. No, Ankur. In the case when instead we can get the smallest from the right subtree and swap, you but if what if the here we are considering the case when the right and the small left both subtrees are null, right? This is a leaf node.
So we reach at the leaf node by recursion.
What?
We reach at the leaf node by recursion now, from the bottom to at the end.
Mm-hmm.
So at that time, if we make that node null,
Mm-hmm.
so that back and return null, then at the back it when it
Mm-hmm.
band is return null, na? When it's back, it's returned to the previous value.
Yes, so we will have to write a new helper for that, right? If you want to do that, like then you are not using the search, which is fine if you don't want to. So you could do that basically. What? So basically, then we cannot use the search. I am just
Yeah.
we will have to write our own recursion here,
Yeah, delete it.
which is fine. We can do that also. Let's do that instead of searching. We could actually use the search, but then we'll have to find the parent you can find by just coming from the root. So that is also one way you could do it, and the other way is if you want to do this searching also here itself, you could search instead of calling it explicitly, and while searching itself you could return. So if you want to do that, then basically you will have to get around this, and what you will do is
So why alt is equal to null will not work
where elt equals null.
when both the subtrees are null, both the childs are null. We just do alt is equal to null.
No, it will not work because elt is a, see, I'll tell you, this is a fundamental problem, which misconception. So see, what has happened is you had some tree you have, let's say this. Now what you have done is you want to delete this element, let's say. So what you did through the search was you came from here to here, then from here to here, from here to here. Now you are here. So once you saw that the value of this node, let's say this was 3 and you were searching for, you were deleting 3 only. So once you found that value, now you have to delete this. So what you do is when in the function, in the call, in your delete function, what you have done is you are calling tree node star ELT equals search, right? So this search is returning a pointer to this node. So ELT is now pointing to this node, right, in this function. So when you do ELT equals null, this pointer changes to null. But this, why will this change to null? You have to change this to null. That's the problem that we are trying to address.
Okay, sir. Okay.
Yeah,
Yes, sir.
you have to change this, not so that's why just changing ELT to null here will not work. The same was the case with insertion also. So you will have to do better. So one way you could do it is you could recursively search here itself. So let's say if your value is less than the root's value, just keep doing this, less than, let's say. So then basically you have to delete from the left subtree, right? So you can just recursively call again. From the mission statement itself I am writing that I have to delete the element and return the root. So this check is basically telling me that the element is in the left subtree. So if it is in the left subtree, then just delete and return. If it is in the right subtree, then just delete and return. If they are equal, so basically now you found it. So then you have to now delete this, right? So now here you have cases. So let's see the cases. The first case is if it is a leaf. So how do I know it is a leaf? If both the left and the right children of this is a null. So if both of them are null, then what you could do is you could simply delete this, and now you can return null. Now this will work. Correct? Otherwise, first of all, do you understand why this will work, why that does not work? Can I have responses from you if you understand why this will work and why that did not work? Yes, I. So think about this case. What we are doing here is, so if you are trying to understand from level 1 itself, what is the definition? We are deleting an element and returning the root of the tree after deletion, right? So I am just trying to be consistent with that definition in the sense that if the current value is less than, then basically I will just change the left pointer, right? So I will make the left pointer point to the new tree, which is after deleting the element from the left subtree, right? And if it is greater, then what I will do is I will make the pointer, the right subtree's pointer change to the new tree, new right subtree formed after deleting the value. That's all I have done. And what is the third case? The third case is if this current element, I'm just thinking level 1 here again. If this current element itself is the node that I have to delete. So now I know the cases that if it is a leaf, then I will delete it. And what is the definition? I will return the root of the tree. So what is the root of a leaf node? The root of a leaf is null after deleting, right? So I am returning null here. Right? Do you understand from level 1 why it works? Yeah. So this is level 1 if you are trying to understand. I will do it, I will show you the recursion tree also. So what is the base? Another base case is if it is null. If root is null, then you can simply, you cannot delete anything, right? So then just return null. So this is level 1 thinking. So just always try to think level 1. If you are able to think level 1, then you're good. I will show you that recursive tree also, and you will get a better understanding as to why this works. Otherwise, so let's move on then. Otherwise, then basically if you have one child, so how do I know if it has one child? Let's write a function. Boolean has one child. So this will return true if I have one child. Okay. If this node has one child, how do I see this? If if your left tree subtree is not null and your right subtree is null, then you can return true. If your right subtree is not null and left subtree is null, then you can return true.
Sir, I think we should return the child rather than yes or no, because if we return yes or no, anyway we have to find if it has a the child is left or right after we find if it has one child.
Got it. Yeah. So basically, then what we could do is we could have an integer which says that this returns -1 if it does not have one child. This returns 0 if it has only left child. Right, Pranav? This is what you are saying, right? If I
Yes, sir.
understand you correctly. Returns 1.
So what I was saying is ki if we could return a pointer to the child itself.
Okay, and you will use that.
Yes, sir.
Okay. Yeah, that's actually a better way of doing it. Okay. So Pranav is saying let's return the pointer to the child. Pointer to the child which is not null. So if left is not null, this is the case. If right is not null, then this is the case. Otherwise, you could just return null. So this returns the pointer to the child, which is. So now I will check if it has one child or not, which is basically has one child. Or let me. We have already returned from here, so it's okay not to write else. So let's call this on this root. Now if so if it has both the childs, then also we are returning a null here, right? And if it has no children, then we have already taken care of the case here. So this is strictly if it has one child. So if this is not null, then it has one child, right? This is the case that we are handling right now. So how do I take care of this? We can return the child. Do you understand this? This is the algorithm we discussed, right? If it has one child, we just return the point, we just make the parent point to that. Correct? So we are just doing that basically. Or at level 1, if you want to think what am I doing? I will delete this node, which is what I am yet to. So let me delete this node, which is delete, and I can return the child. So what is the level 1 definition of this tree? This is a tree wherein you have one node and one of the subtrees is not null and the other subtree is null. So how will you delete that kind of a tree? You will delete the root node and you will return the pointer to the subtree which is not null. So that's basically what I have done here. Level 1 again level 1 thinking only. I have not gone beyond level 1. Do you understand this? Like from level 1 thinking, do you understand this? Can I have some responses? Yeah. So if you don't, let me know. I can repeat level 1 thinking again. So then finally we have the last case, which is basically if both children, this will be children and not child. I used to write it as child, then somebody corrected me. So if both of them are children, then both children are there, then we will have to, what is the algorithm? We have to find the, either you could find the, we can find the smallest element greater than this element, right? Or we could find the largest element smaller than this. So let's find the smallest element greater than this element. So this basically is called an in-order successor of this element, which is fine. We will talk about in-order successors when we discuss binary search trees in more detail, like when we do recursive questions on them. So for now, even if you don't understand then that, it's okay. We are basically just finding the smallest element greater than this element. So you will find it in the right subtree, right? So let's do that. Let's write another helper, which is get. I want to write in order successor, but if you will question me then, so let's write get smallest greater than. So this is the root and this is the element. So I could do iterative, I could do recursive, and right sub, sorry. I have to go to the right subtree and I have to go all left, right? So right subtree is this, and then I have to go all left. So as long as I don't encounter a null, I can keep going left. But because I have to return, so I will do this and then I can return this, right? So this is basically the element. So ask me questions if you don't understand this, but I think it is fairly straightforward. So now I will use
Sir,
this
what were
function.
you doing there?
Yeah, so basically we just moved on to the right subtree and then we keep on going left until we reach null. So basically we keep on going left until the node at which we are presently, that node's left is null. If that node's left is null, then that is the smallest element greater than this node, right?
Okay.
Yeah. So we
Yes,
are
sir.
just doing that. This is just keep going left. So I could find that. Let's call it successor. I am not giving in order name here. So I just got the successor of this. What will I do now? I will swap both of them, both of their values basically. So I can use inbuilt swap functions for that. So basically I will swap this value with this. Now I have to delete this, correct? So now how do I delete this? I could free it, but the problem with that is that the parent of that node now, will it have null? No, right? So how do I delete this now? Do you understand the question? Now I just have to delete this leaf node. So how do I delete this leaf node? Any ideas?
We can call the recursion. It can.
So let's think level 1 here again. You have to delete the current node, and you know that both the subtrees are not null. So what you did was you just found the root, and you, so what Akash is saying is that you can call delete again, this function itself, right? This is delete node, let's call it, because delete is a keyword. That's okay, but I think it will be fine. So Akash, you are saying that I call delete node again.
Yes, sir, because it converted into a leaf child, leaf node problem, right?
Yes, you're right. But that is okay. But how will you? So that will basically. So what you are saying is, now let me call. I will say that this current pointer will point to now delete node from the root itself, but now this value, right? The on this subtree now I can delete this node. That's what you're saying, right?
But in the swap function, shouldn't it be successor's value rather than root's successor? Because both of them are.
हाँ वो गलत है हाँ अरे वो मिस्टेक वो बस typo, that's a typo. So Akash is saying do this. This is right. This is a very smart way of doing things. Okay, and finally you can return root. So this is the delete function. Now ask me questions if you don't understand any of this, like at level 1, or if you want me to show you explain something with an example, please let me know.
So that a root of right equal to delete node, like line number 92, that function, if you could.
Yeah, let's see that in action. So let's try and understand what we have done here. See, you had a tree. Again, I will draw a tree. Let's make this big. Yeah. Let's say you want to delete this node. Okay, so what did you do in the delete node function? in the delete node function, what you were doing is you started from here. You saw that the value is left to the left, so you came here. Then you came here. Now here you found a match for the value. Okay, so now you have to delete this node. So currently your root is here, the pointer is here. So you have called delete node on this node. Now here you do that check that if both the children are present or not, which returns true. So now you have both the children here. So what do you do first? You return, you have one pointer here, which is the root. I mean the local variable root. So don't take it as the root of the entire tree. Now what you do is you go ahead and you find the in-order successor. So you go here, 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 and you get successor. So SUCC points to this node. Correct? So let's say this is 3 and this is on the right subtree. So let's say this is 8. Okay. Now what you do is, now you want to delete. So what you do is now you swap both of these. So now you have 8 here and you have 3 here. Now what you have to do is you have to delete this node. So isn't this problem the same as deleting 3 from this subtree and returning a root to it? So what now I am doing is I am saying that call delete node on this subtree. So call the same function which I have written, call it on this subtree. So on this subtree as in on the right of root with the same value, with because I just swapped the value, right? So with the same value, call it. So what will that ensure? From the mission statement of this function, I know that this will basically delete the node for me and it will return a pointer to the root. So the root, whatever the pointer to the root is, I am here, right? So I will make the right of this node point to whatever is being returned here. So I'm just using the mission statement to do this. So now this will basically, this right will point to the tree which you get after deleting this 3 from this tree. And I have just recursively used the same mission statement. So the same function again, because the problem is the same now. Right? So now when you call it, it will start from here and it will start the entire process, this entire function again, whatever I have done. And here somewhere it will keep searching. Here somewhere it will find that, oh, this is a leaf node or one child node. It is at least a leaf node or a one child node, right? It cannot be two childs. At least the left child of this successor is null, that you know. So it is, in both the cases, it will either return null or it will return the pointer to this. So this will then point to either null or this subtree. And then it will keep returning recursively till you reach here. From here, you will return the root of this. So you will return this node. So this will now point to this node again. And this has been freed also. Do you understand this? Like both, I just try to, like in a very fast, I just try to explain both in both the ways, level 1 thinking as well as the recursive unfolding.
Sir, how again it constructs the BST by the satisfying the condition after deleting?
That's a good question. So what Jadav is asking is that after swapping the node, you are calling delete node on a BST, right? So this has to be a BST after swapping. So can someone tell me, is this a BST after you swap this with this? No, right?
Are we swapping the elements itself or the nodes?
We are swapping the elements, the values.
Okay.
Is this a BST? Ankur is saying no. What about others? No, I have not said whether it is yes or no. I'm asking you. What do you think? Just take a guess, like an informed guess. It is still a BST, right? Why do you think, Ankur, it is not a BST? So what you have done, let's think. You have basically replaced this element with the next greatest element. So what is the problem? The problem might be with this node, right? So every other node in this half, so I am not, obviously I will not be concerned about what comes. So let's talk about its parents. So for these nodes, you know that these nodes in its path, you know that definitely these nodes are greater than this node, right? Because they were all coming because this is the smallest node in this tree also now. Because why? Because you found the smallest element which is greater than that, and you swapped it with a smaller value, right? So now you, whatever value you have here is smaller than what it was before. Previously you had an 8 here, now you have a 3 here. So for all these parents, the BST condition is still met, right? Now the only problem is, let's think about this tree, if there is a subtree. So now because you have replaced it with a smaller value, if 8 was smaller than this subtree, then 3 would also be smaller than this subtree, right? So for this tree, this subtree is still a BST even after swapping. So that's why you can call this delete node on this subtree again. If it wouldn't have been a BST, then you cannot call, because the mission statement itself violates. Your mission statement is that I am taking a BST as an input. Does everyone understand this? Here, in this case, or generally, Karan? In this case, right? So in this case, what I'm saying is, once I have swapped, till swapping, there is nothing. Till swapping, I'm just using the algorithm that we devised yesterday. After I have swapped it, basically my problem statement reduces to deleting this node from this subtree, this entire tree, which is also equivalent to saying that I have to delete this node from this subtree. And that's one thing. So I am already, and this subtree is also a BST. I know that even after swapping. So I know that I already have a function which does exactly that. What does it do? It deletes a given node from a BST and returns the root of the node. So I'm saying I might as well reuse that function for this. So I have just reused that function wherein I have passed in a subtree and a value that I want to delete. And once I delete it, I know that this function will return the root of the new tree. So that root of the new tree has to be the right child of this node, right? So I'm just making the right child of that node point to the root of the tree after deleting the node. Okay, so everything in a BST is clear. I will just show you the code again. So insert, delete, and search. Are all the three clear to everyone? Can I have a milestone acknowledgement before we move on to heaps? Like clear as in how you created it. So you should be able to write it on your own. Just so I did not, so it's been a while. It's been about 6 to 8 months since I wrote these codes. But I just know the algorithm. And the reason I'm able to write this is because I have that level 1 thinking through which I just write it. I just define a proper method statement and I abide by that in the definition of the function. That's it. So that's why, if you remember all the recursion lectures that we did, we were stressing a lot on this, on the prototype and the mission statement, because that is the crux. If you are able to define a prototype and the mission statement which solves the problem, then you can implement it. Implementation is not a big deal, like just abiding by it. But coming up with this prototype is crucial. Coming up with this idea that I have to return the root of the tree is crucial. If you use a void here, then it will all be messy, the code. So that's basically the whole point. So if there is one takeaway from this exercise that we did in the class, it is level 1 thinking. Binary, we will do dynamic programming. There also I will show you, like numerous times we will just do level 1 thinking, because they are all recursion after all. Shall we move on? Let's move on to heaps then. Clear to everyone? Anyone has any question? Any part you want me to repeat, or any specific section that you want me to dry run with an example? Please let me know. Otherwise we will. Yes, Karan, this is the insert function. I will.
Insert function, is insert function used as keyword here?
It is so, but the problem, it is, but it will not match any library function, because you have the parameters, the type of the parameters is different from what library functions take, right? So what it will do is it will, I mean, it might do different things. So the safe bet is you could write insert node, like write a custom name. But I have a hunch even insert will work because of function overloading. If you know function overloading, what is function overloading? If you have the same name but different arguments, if you have two functions of the same name but different arguments, then the compiler has a way of figuring out which function to match, right? Here the name is insert, but the parameters are different. Here in the arguments you have an integer and a structure which is your own defined structure. Any other library function will generally not have this. So it will still be able to resolve. This is the delete code, Pranav. I can make the font smaller so that it fits. Yeah, now it fits. All right. So if this is done, let's move on to heaps very quickly. So let's call it heap implementation. You could do CPP files, you could do C++ files. Both are fine. Yeah, I will just I will upload both. I will make sure. Good that, I mean, thank you for reminding. Good that you reminded me. I will make it a point to upload both of them. Okay. Okay. So let's talk about heaps now, finally. So let's do heaps. So here, when we are coding heaps, we will use the array implementation for heaps. So let's just say you have an array with some numbers. Just now bring your mind to heaps. Like, so let's say you have some random numbers in the array. Let's say this is an array. Now you want to convert it to heap. Then let's say you will delete some elements. Let's say you will get the minimum. I'm just delete the minimum. And let's say I will insert an element as well. That's it. Insert, delete. And let's say we will do heap sort also. I will show you heap sort also with this. So sort the array. Let's say we want to do all these. Okay. So first things first, I will just write the heapify function. If you remember, So what we used to do in the heapify function was that we used to assume that both the subtrees are heaps and it's just the current node which is not in the right position. So we used to say that we will basically make this entire tree a heap. Okay, so that's what we want to do in the heapify function. So let's write the heapify function. Let's say these are all min heaps. First of all, you could use a vector. I'm just using an array for now. And let's say I know the index from which to heapify. Okay, so index is basically one of the nodes. So what was the logic? Can someone tell me? I don't know why today's class is such a monologue. It's all me speaking and you guys.
Sir, I couldn't hear before this. What's the question? What's the thing you told before void heapify thing?
I'm just saying that first thing, let's write heapify function, like because it will be used as a subroutine in many of the functions that we implement. So we just want to write it first. That's it. So I'm just asking what is the logic? What was the logic of heapify or the algorithm behind heapify?
So compare I 2i plus 1 and 2i plus 2.
Yeah. So compare it to the child's and swap if it is not the minimum, and then heapify on the child, right? So the first things was, so what will be the left child of this? The left child of this will be, we are all doing a zero based indexing, so 2i plus 1, and the right child would be 2i plus 2, correct? So what I want to do is I want to find the minimum of these three. So for that, let's say I have this min element. So let's say I take the minimum of the current node with the left child, whatever is the minimum. And then I mean, you could do it in one step also, which is fine with the right child. So now I know. So if this minimum is this number itself, in fact, let's find the min index. Right. So now, if this minimum index is the index itself, then you can return, right? Then it is already a heap. Again, I'm writing recursive function. So again, level one thinking, I'm just saying that if the current node is already smaller than its left and right childs, then this main index will be equal to index, right? So then I can return this heapify is, I'm done with the heapifying. Otherwise, I will basically swap, right? So I will swap the current index with the minimum index, and then heapify, again recursive logic, the same array with starting with this index. Correct? Will this work?
Sir, in the when we are doing in lines 7 and 9, will not min index have the value at index or the value at left or right? And then we are equating it to the index in line 11.
I got you. Right. Now this is fine, right? Pranav? Yeah. So Heapify, everyone understands? Just one base case is there are cases which you need to take care, which we haven't. Here you have to check if L is within the range and if R is within the range. So array has a size, right? Which you will need to take as an input if you don't. And you have to take care of those cases as well. So because this could go out of range, right? Out of N. Then you will get an out of bound, array out of bound if you are accessing that element L. So you need to take care of those cases. So one way you could do it is you will make it point to the index if L is, so if there are many ways you could do it. I have just done one. So with this, basically I'm saying that if my left child is greater than equals to N, so basically my left child does not exist. If either that is the case or I am the smaller out of the two. So if that is the case, then it will return true, it will not go here. So it will then my min index will be index, otherwise it will be length. So similar thing I can do here also. If my R is greater equals N, or this, then basically this, otherwise this.
Sir, what is the value of N there, or what is N there? Like any element.
Come again.
What is N?
N is the size of the array.
Okay.
And these are indexes. Yeah, this will be fine. And you could do one here, that if your IDX is greater equals, and then you can return. Cool with everyone, this logic to Heapify? Can I have responses if it is fine? Yeah, all the cases have been taken care. There are no other corner cases, right? Okay. So now let's then do these things. So how do you convert it to heap? If you remember, what were we doing? We will basically start from n by 2. We could go up to 0. And what we will do is we will just call heapify. So n, just take n, right? how much, what is the count here? Just, I mean, make it dynamic, but I don't care right now. 9, right? Heapify on I with n. So this will basically convert it to heap. And this is basically the make heap. This is order n. Right? So this is the make heap. If you want to return the minimum, so this is basically array of 0. So let's say you print this. Right? Now let's talk about deleting the minimum. So how do you delete the minimum? You can take the array with array has 2 parameters. You will simply, what was the algorithm for deleting? Can someone tell me?
Swap A0 with n-1 and call heapify on A0.
Yeah, so you could just swap the minimum with n-1, and then after that basically you will have to reduce the size of the array, which we will do here. I mean, you could do it either ways. Now again you will basically heapify so now you will heapify on this node, right? So heapify the entire array starting from 0, but the size is now n-1. Okay, so this will delete the minimum for you. So you could delete the minimum. You will have to do an n-, here. So now let's say if I get the minimum again. So next minimum element is this, right? Let's talk about sorting the array before we come to insertion. Insertion, you will have to write your own code. So for sorting, what is the way you could sort this array? You could just keep taking minimums, right? Every time you take a minimum, delete it, take a minimum, delete it, right? You will be able to sort the array, right? Do you understand this? So let me write heap sort for you now. So you have this array. What will you do? What is the algorithm? Algorithm is get the minimum, delete it, and repeat, basically. So how would you do that? You could start from 1 to n-1, or so you will do it this for n times and you will be able to get the array, right? So get the minimum, which is nothing but array 0, right? And actually let's store, you will have to store this because we will reduce the size dynamically. So get this element, then what you do is you can remove this element. So see out this. Now you will remove this element or delete it. So you could do a delete min the array with size n. Once you delete it, do n minus minus to say that the size has reduced, or you could point it by pass it by reference and delete, decrease the size here. So now, and then you will repeat again. So again, get the minimum, and so this is basically heap sort for you. Do you understand heap sort, or should I make it more explicit? Can I know from you? Like, why are we deleting store? So we are just extracting the minimums, right? We are not storing, we are basically moving it to the end of the array and reducing the size dynamically by 1 every time we delete it. So this is get minimum, this is printed, this is delete the minimum. Others, do you understand? People who are new to this, do you understand? Right? So sorting is taking place in the delete itself, Jadav. When we are heapifying, you are rearranging elements again so that you are bringing in the next minimum here again.
Okay, okay, sir.
Yeah, so others also understand, right? So this is basically the heap sort. So let's do sorting before inserting. So heap sort with array and the current size. So we will insert it, but let's quickly run the code. Where am I? Oh, I'm in the Oracle server. Okay, let's open a local server. So I am here, heap implementation. This is the file. Let's compile it. It will not compile because I don't have any headers as of now. Let's quickly have some headers. If you really want, just include everything. If you want to include specific headers, that also you could do. So let me just share the terminal with you guys. So now if you see, I have this file here. I will just compile it. It generates that error, which is basically the namespace. Yeah, namespace is also the issue. Other than that, I think Mac's default compiler does not understand that also, like bits std also. So I think we will have to take care of that also. What else have we used here? We have used this. We have not used this, but stdio, std lib, right? Lib also we have not used, but it's okay. Let's see if we need to include any more headers. But I think we should be fine. Let's see. So cout is which part of which library? IO stream, is it? What is the library for this? Guys, IO stream, right? It's been a long time. SOP is a part of some function, I guess, Savio. We will see. So you're saying SOP also we will have to implement, or you? I think it is a part of maths. It only does not understand cout and end line. So these are all part of IO stream only, I think. So it is not able to link basically. So what that means is that there is some call which there is some function which has a conflicting implementation here. Which is, it might be what is the algorithm header for swap? You're saying swap is screwing.
No, sir. The header is algorithm. It's called algorithm.
But it compiled fine, right? So it understood swap. So if it compiled fine, I think it understood. There is some issue with these might be library names also, right? So that also could be issues. You could just do an underscore in all this. Want to just get. So EP5 is fine then. EP5 here. Let's try it one last time. Otherwise, we will use the online ID as Akashi suggested. Okay, let's use online ID. This works. Now you have the .out file, right? April 25, 8:45 a.m. This is the file, right? Yeah, this is, yeah, 8:25 a.m. 8 April 25. Yes. So let's run this and let's see if we get any segmentation faults. So we don't. So you see, we inserted what was the minimum element is 1. After we deleted it, the next minimum is 3, and this is the heap sort output. Okay. Is this correct? Clear? Let's quickly finish it with the insertion. So these were the elements. You could go ahead, go back and cross check. It is fine. So let's finally insert an element in the array or in the heap. So this is the insert function. So let's see, and you get the array. So what was the algorithm for insertion?
Insert at last and then heapify.
Insert from last and then heapify. So heapify or just swap it with the parent, right? If they are not in order. So what we will do is, of course, this will assume that you have enough array. So what you could do is you could just put that element at the end. And now what you will do is you will swap parent of n with n if not in order. Okay. So what is the parent of n? N's index. What is the parent of n's index? This will be n by 2, right? Or will it be n by 2 or ceil of n by 2?
So yesterday you mentioned floor of j by 2 for parent.
Floor of j by 2. So just doing j by 2 will be fine. Or will it be floor of j minus 1 by 2? So my question is, for an index j, what is the parent of j? J minus 1, right? Yeah, for 0 based it is j minus 1. So what we will do is, while I have a parent, okay, so what I will do is I will just check if, so while parent is greater or equal 0, which is fine. So if array of parent is, if that element is greater than this current index, that means I will have to swap, right? So I will swap both of them, and I will,
So shouldn't it be n minus 1?
where?
ID equal to n minus 1.
No, we are inserting at the nth index.
Okay.
Yeah, we are inserting at the nth index. The last, one more than the last, right? Here we will assume that the array has enough size. So don't get confused with the n. It's just the size of the array. So I'm just inserting one size of the heap. We are assuming array is bigger than the heap. So we swap it, and then our parent basically becomes parent of parent, right? So what we could do is we could just do a get parent, actually. Get parent for an index is nothing but return so then I could just do a get parent of n to start with. So then my parent becomes get parent of parent. Right? And if it is equal, then what I could do is I could simply break. Yeah. So this insert is fine. I will do another. else here. Otherwise it will always break the first time. So basically, Karan, if it was less than, if the parent is less, then things are already in order, right? For a min heap. So I can stop going up. So I'm just I just keep going up till I reach the parent or till I stop swapping. So I have just implemented that logic here. So if this is fine, let's see. So we have removed one element. So we can afford to insert one because the array has that size space, right? So I think we can insert one element. So let's insert which element. We removed one, right? The minimum. Let's insert 5. Let's insert 5 for some reason. I don't know why. And the current size of the heap is n. You have already reduced it. So let's insert it and then let's sort it again. After inserting, you will have to increase the size of the heap, which is what I do, and then I can sort it again. So let's see if this works. So I should have put a delimiter somewhere. Let's do that also. Just do a let's just print the same line twice. So apparently insert didn't work, right? Yeah, so insert apparently looks like it didn't work because I printed, this is sorted till here we are fine. This is after inserting 5. So from this we inserted 5 and now we are printing it. So I think there is some issue. So I will share the code with you. Just take a look at it. I think there is some issue here. I did not update the ID, right? So ID will be parent for the next cycle. It is still giving you some issue. Okay, we will see. Let's not spend more time on this. I will share the code with you, or towards the end of the class, we can debug why insert is not working. If you are like able to figure out, I mean, maybe 5 seconds from now, then we can debug. Otherwise, let's move on. Okay. So this is basically all the heap functions as well as all the BST functions. I hope you get an idea, right? What? Shall we move on? Is this fine? Like, does this help? This is fine, right? The entire code of all the functions. All right, so let's move on to better applications. So now let's talk about applications again. So let's move on to applications. So so far what we have done is we have talked about unordered structures, and now we will basically be looking at problems where there is a need for ordering. So we need the minimum in some way or the other, and that's basically what we will be concerned with in the next half of the lecture. So let's start with a problem, which is this. Try this question. So this is question number 209. So what's going on in your head when you see this question? So remember the view of the subarray that I gave you in the last to last class? Does something strike with that? So first of all, tell me, can you apply 2 pointers here?
Yes, sir.
Okay. So what will you do in that? Why do you say that 2 pointers can be applied here?
Sir,
So you are given an array and you are given an array with numbers. What you have to do is you have to find the minimum window or minimum subarray with sum equals to k, right? Yeah, we can apply 2 pointers here. Tell me two things. This question tells you that this array has only positive numbers, okay? So what if the array had negative numbers also? In that case, could you have applied 2 pointers? Why? So my question is that currently in the question you are given that the array has only positive numbers. So you said that yes, we can apply 2 pointers. I am just modifying the question. I'm saying, what if the array had negative numbers also? Can you apply 2 pointers then? Yeah. So you cannot apply 2 pointers if the array has negative numbers also. If it has only positive numbers, then here you can apply 2 pointers. That's basically, so here it is applicable. In this case, it is not applicable. Why is it that way is something that I will leave to you to figure out. So just think about it and let me know. We will definitely discuss this tomorrow first thing, like if we have a class tomorrow, that why is 2 pointers not applicable if we have negative numbers also. But today I don't want to solve this question. So I am taking this question only wherein we have positive numbers, and I don't want to solve it with 2 pointers. I want to solve with an n log n approach. Let's say the question is just given you that. So how do you go about applying an n log n or thinking about an n log n solution? So let's see. So first things first, if you remember, we had so subarrays, I told you, you have certain cues. When you look at subarrays, you are basically thinking to either 2 pointers, or you are thinking about the view of the subarray that I gave you, right? Which is basically, I'll just repeat it for the sake of completeness, that every subarray, you can, let's say this is the subarray, you can represent it as this entire prefix array minus this prefix array, right? So that's how you represent subarrays. So we want to use that idea in this question also. So how do you go about thinking? So obviously my subarray with minimum window subarray with some k will be basically minimum of subarrays ending at 1 with some k, subarray, minimum subarray at 1 ending at k with some k, comma minimum of subarray ending at 2 with some k, 0 also you will take ending at 0, and so on, right? So you will basically enumerate for every index. If that index is the ending index of the subarray, then you will find the minimum window subarray with some k ending at that particular index. And this you will do for all the indices. So for this index, you will assume that if the subarray ends at this index, what is the minimum window subarray with some k? Then you will find the minimum window subarray with some k for ending at j plus 1, j plus 2, and so on. And you will take the global minimum across all, right? That's basically the view of the subarray that I told you. We are just using that. So now let's talk about the second part, which is basically once you have decided an ending index for a subarray, and you are saying that my subarray will end at index j, how can I define the property for a prefix array? Right? That's what we had in step 2, right? We wanted to reduce the problem of finding the minimum window subarray ending at j to finding some prefix array with some property before ending at before j, or right? That's basically what we want to do. Till here, is it clear? Like, is the story synchronous with what we have discussed so far? Like day before yesterday? You're following, right? Is there anyone who did not attend those classes and does not follow this? So now this is the property that I want to find for this prefix array. So let's say this entire sum is S again, and this is K. So I want to find prefix array with some S minus K, right? That's the property for the prefix array. With some greater equals as it is said. So let's define the property. So you want to find the minimum subarray with some greater equals K. That's the question. It's not equal to K. So let's say this sum is S, this sum is Si, and this is I. So you want to, your S minus Si is basically Sj, and you want this sum to be greater equals K. So what do you want? You want to find the minimum length. Minimum length. So you want to find the minimum I also, or maximum I. Maximum I, right? So the property is, so in the original question, we want to find the minimum length subarray with some greater equals K ending at J, right? So I'm just saying that that problem has reduced to finding the maximum length prefix array. Maximum length prefix array, so that this becomes minimum. Maximum length prefix array which satisfies this property, that if you subtract S from that sum, it will be greater equals K, right? So this basically comes down to Si is less equals S minus K. Yeah, you can use the binary search because it is sorted. So what is this now? So now once you are at the given J, what do you have to find? You have to find the first I from the right, right? The first I from the right which satisfies this property, that you have to find the first I such that the sum of this array is less equals S minus K. Correct? Is this clear so far? The property for the prefix array. Do you want me to repeat any part of this? So now tell me, how do you find this? So now the problem is, for a given J, I have to find this I. First from right, because I have to find the minimum window, minimum length window.
So what was Si exactly?
Si is the sum of this prefix array.
Which one, the left or right? It's a little confusing.
Si is this.
Oh, okay.
And this entire thing is S.
Yes.
So I want this sum, S minus Si, to be greater equals K. And why is it the first I, first from the right? Because we want the minimum window, minimum length window.
Wouldn't it be first from the left?
If you get the first from the left, it might be you might still get another window which is whose sum is less equals S minus K, but that would be the minimum for this, right?
Or the last window from the left. Okay,
yeah, okay. Last window from the left or first from the right. Correct? So now the question reduces to, for a given J, I have to find this I. So what could be the possible ways of going about solving this? Can you do binary search? Why? But the prefix sums are sorted, right? You will do a binary search on the prefix sum. Do you understand? Do you see what I'm saying here? Because it is all positive numbers, the prefix sums will be sorted. So you can do a binary search also. Apart from that, other than binary search, there is another way you could do it. So remember what we used to do previously in the questions from hash table. what did we used to do when we had to, this is an evidently a searching problem, right? So you have to search from all the prefix arrays, all the prefix sums that you have already encountered. That is your search space, right? So you have all the prefix sums, ps1, ps2, ps0, all these are there in the, and you have to look for one such psi with this property, right? So these prefix sums, what if I store it in some search container or in some search structure which allows me to find this? So here I have to find, right? So that's the idea that I will use here in the second approach, that what, because I have to search for a prefix sum, why don't I keep adding prefix sums to a container, to a search structure, and which enables me to search efficiently, and I will insert also on the go as I am going, right? So let's talk about the search structure which can allow me to do that. Hash tables are a big no. Why? Because what do you have to find? You don't have to find an exact match of a prefix sum, right? You have to find a prefix sum upper bounded by sub quantity, right? You have to find a prefix sum which is less equals some quantity q which is given, which is some constant for this given j, right? So there is an ordering. The container, if it is not keeping these elements in an ordered fashion, there is no way it could search and give you this in an ordered, in constant time or in an efficient manner without actually having to linearly traverse the entire container, right? So hash tables are a big no. So then we will look for ordered search structures. So tell me this, what if you had these elements in a binary search tree? If you had these prefix sums in a binary search tree, can you find a node with some s minus k? With some upper bounded by s minus k, the largest. So what do we have to do? We have to find the largest. How do we do that? So first of all, do you understand why hash tables are a big no? And do you understand this idea that I am looking for something, so I might as well use a search container where I could keep it? Yeah. So now I am debating on the search container or the search structure that I can use for this purpose. And that's where I am talking about what can I use. So imagine I already have an array. So let's say all these prefix sums are increasing, correct? So if these prefix sums are increasing, what does that mean? That means that if you have this prefix sum, let's take two prefix sums, pi and pj. So if I is less than j, then pi is also less than pj, correct? So this problem of finding the first I, so this was j actually, and we have to, so now this is the property that holds. Now let's come back to the original problem again. So for a given j, you have to find the first I from the right such that this sum is less equals s minus k, right? So isn't this equivalent? So I have to find the largest I, right? First from the right, as in the largest I. Let me write this. So what I have to find? I have to find the largest I such that pi is less equals s minus k, right? That's what I have to find. So isn't this equivalent to saying that I want to find the largest pi such that pi is less equals s minus k? Because of this, Do you understand this? So I have done 3 things so far. Just to summarize for people who have lost me. Yeah, because it's sorted, because the sums are increasing. Where, Karan? Here you are saying? So finding, yeah, tell me.
So in the PI less than that, here that we are considering, which subarray we are considering in this case?
So see, when I am at a J, I have to find the largest I, right? Largest I as in the first I from the right, which is basically the largest I, which satisfies this property that the prefix sum is less equals s minus k, right? So what I'm saying is, as your I is increasing, your pi is also increasing, right? So let's see this. This is I, this is pi. As your I is increasing, pi is also increasing. So you have to find one cutoff I for which this pi is less than s minus k. So s minus k is somewhere here. So you put all these i's, I1, I2, I3 on the number on this line. Where will they be? I1 will be here, I2 will be here. Let's say I1 is this, I2 is this, I3 is this. So you have to, coming from the left, you have to find the largest I, which is just below this s minus k, right? So isn't this equivalent to finding the largest sum, largest pi, which is just less than s minus k? Right? Because it's an increasing function. Otherwise, that is not true.
Sir, I was saying that you have written I less than j. It should be I1, I1, I2.
I1 here, right? Matlab wahi, if this is another j. Yeah. This is another j. This j is different from that j. Okay, keep it I1, I2. Yeah, you're right.
Sir, why we are worried about largest I here? Why we are?
Because we have to find the smallest window. It's given in the question.
Okay, got it.
For every j, we have to find the smallest window with sum greater equals k. Right? So I have told you 3 steps. I just told you that we will use the view array view that we have discussed. So for every j, I have to find the I. The property is that I have to find the largest I such that pi is less equals s minus k. This is the property for the prefix array from the subarray. And from here, I said that this is equivalent to saying that I have to find the largest prefix sum, which is less equals s minus k. So why did I go from I to pi? Because my container has pi's, right? So that's why what I did was I reduced the property in terms of pi. I'm just telling you the thought process. My container has all pi's. I have to look for a pi with some property. So I did find a pi. Did find a property for the prefix array, but that still was in terms of indexes. So I made this observation and I reduced it completely to a pi. So from this container now, which has all the pi's, I have to find one pi, which is as large as possible, but still less than s minus k, less equals s minus k. So now, so this is, I have done step 2. Now let's talk about the container, the choice of the container. So my question to you is, if you have a binary search tree with all the prefix sums, you have a binary search tree, and you are given a quantity s minus k. Let's call it, this is a constant, right? Let's say call it c. You are given some c. Can you find me the largest pi from this binary search tree which is less equal c in log n time, assuming this is a height balanced tree? Can you give me an algorithm for this? Do you understand the question? I know the container now. I am just brainstorming on the choice of the container. So I'm thinking, is it possible with a binary search tree? Can I search for this pi from this binary search tree in log n time without having to go through all the elements?
Yes, sir.
How will I do that?
So we use the property of the BSC.
Okay.
First, we're finding an element which is less than equal to C. We keep traversing the left subtree and appropriately adjust. It would be a simple recursive function, I believe. That would have accomplished.
Yeah, it will be a simple recursive function, but like
it's searching in a BSC in its simplest form with the condition of less than.
With a condition of less equals. That's basically why I'm asking the question. It's not exactly equal, right?
Yeah.
So how would you do that? You
will
could
just store the previous result.
Yeah, you will have to keep storing the minimum.
Another variable in the same function to introduce like a previous container type variable, and once the sum exceeds that value, we can obviously break the recursive function and return the previous function.
Yeah, that's right. So you can just make a slight change in the original search for a BST to be able to implement this. How? You compare P1 with C. Okay. Two cases, either P1 is less equal C or P1 is greater than C. If P1 is greater than C, then you can discard this entire subtree and move here. Okay. If P1 is less equal C, you just keep a variable minimum, largest minimum, let's call it. What you can do is you can make it equal to P1 to start with. Okay. So P1 is less equal C. You are looking for larger values of, so now you understand you can discard this entire left subtree, because anything which is in the left subtree, if P1 is less equal C, will be less than P1. So even though it is less equal C, it will not be greater than P1, right? So you are looking for the largest such PI which is less equal C. So you can discard the entire left subtree now. If P1 is less equal C. If P1 is greater than C, then you can discard the right subtree. Correct? So now you can come to P3. Now you check P3 with C. Let's say P3 is less equal C. So if P3 is less equal C, you can update P1 to P3. Or you can update P1 to maximum of P1 and P3, which will be P3 in this case. Right? And once you have updated it, you know that you can discard everything to the left subtree of this, because those will be less than P3. So you have found a value which is already greater. So you can discard the left subtree and you can continue in the right subtree. If P3 is greater than C, then what does that mean? That basically means that this entire subtree can be discarded. You will not update. If P3 is greater than this will still be P1. But now you can discard the entire right subtree and continue the search on the left subtree. Right? So you can keep doing this till you reach a leaf and keep updating your largest minimum. And you will get by the end of the traversal, you will get the largest minimum here, which is less equal C. किसी को समझ आया ये algorithm?
Sir, shouldn't the complexity should be n log n?
Why is it n log n? You are just traversing once from root to leaf. It is height, order of height, right? Why did you say it's n log n? For a given j, I have just fixed a j and I'm searching for an I, right? From the question. The overall complexity of the entire question will be n log n, yes. If that is your question.
Okay.
Is this algorithm clear to everyone? Others? Yeah, Tulika, I can repeat. This is actually important. People, this has been asked in interviews. Can you get me the element which is as large as possible, but still upper bounded by a constant or a quantity? So think about what the decision at every node, Tulika. So what will you do if you compare P1 with C? If P1 is greater than C, then you definitely know that nothing in the right will be a candidate, because you have to find PIs which is less equal C. So you can eliminate everything from the right half. So you can continue your search on the left subtree, right? And if P1 is less equal C, then you can update your largest minimum that you have encountered so far to the maximum of whatever you have encountered, comma P1, and then continue the search on the right half. Why? Because in the left half, everything is less than P1. So you have already found a valid solution which is equals to P1. So any valid solution from here will definitely not be the largest minimum. So you can continue your search to the right and again check for P3 now, and so on. So at every step you can reduce your search space by one branch. So there will be a time when you will reach the leaf, and this will be order height algorithm. So height for a balanced binary search tree is log n. Did you get it, Tulika? Or yeah. So this is the algorithm basically. So then the question is done, right? So then what? Let's come back to the question. So now from this I trace back and I say that my choice of the container is justified because in logarithmic time I am able to search. Let's come back to the question. What was the original problem? For a given j, I had to search the largest pi, which is less equals s minus k. So from all these PIs, from this, all these PIs, I had to search the largest PI, which is less equals s minus k. So if I would put all these PIs in a binary search tree, then I can search for this in log n time. So once I do that, I will have the largest, the smallest subarray ending at j with some greater equals k, right? So I can update my result array to be the maximum of to be the minimum of whatever I have encountered so far, comma the length of this subarray, and then I can move on to j plus 1, right? So this is how I can do this. So that's the entire algorithm, which takes n log n time. Is the algorithm clear? Then I will show you how it is implemented in C++, STL. How can we use STL to implement this? But is the algorithm clear to everyone now? And log n and what we are doing at every step? Okay, I will take it as a yes then from everyone else as well. So then now if that is the algorithm, so let's see how you could do it in STL. So you know that you could keep a map. I told this yesterday, right? In a map, you could, so as you are at a given j, you could store all the prefix sums in a map, right? So you store P1, so M of P1, M of P2, you could store all the prefix sums. So in a map, so with C++, the way you can find such an element is, I will tell you two functions which work on ordered containers, which are lower bound and upper bound. So now listen very carefully. If you lose focus, you might lose. So there are two functions available in C, because this is not a straightforward search for a PI, right? So you cannot do m.find of PI, right? You have to find with some property. So C++ provides you two additional functions to search in ordered containers. Map is an ordered container. So it provides you two functions to search in an ordered container. So what are these two functions? So if you order, so the ordering in a container is always by the key, first of all. So take this like once and for all. The ordering in an ordered container is always on the basis of key for a key value container, for a container that stores key value pairs. For a container which stores only single element, then the ordering is on the basis of that. Okay, so that's the first thing. So ordering is always on the basis of key. So now so what lower bound and upper bound tells you is that if you do m dot lower bound with some value, then what it does is, let's say all the elements of m, if you were putting them on a number line, these are the elements. Okay, so, and let's say this is the range, these are all the elements which are equal to val. Okay, so m dot lower bound gives you the largest such key which is less equals val. So m dot lower bound will give you this. M dot upper bound gives you the largest such key, the smallest such key which is greater than val. So m dot upper bound will give you this. Is the lower bound and upper bound clear to everyone? Yes, I. So basically, on any ordered container, if you do so I'm just telling you about two functions which you can use on ordered containers. So ordered containers are sets, maps, multi-sets, multi-maps, sorted arrays. These are all ordered containers. So in an ordered container, you could do lower bound and upper bound. So if you put all the elements of the container on a number line, let's say this is how they look like, and these are the elements which are equal to val. These three. Let's say this is the range which is equal to val. These numbers are equal to val, and these numbers are less than val, and these numbers are greater than val. So m dot lower bound basically will give you this number the first time the val occurs, and m dot upper bound will give you this one more than the last time the val had occurred. So it gives me the smallest number which is greater than val, and m dot lower bound gives me the largest number which is less equals the val. If val is not present, then it will be this largest number less equals val. Not the largest number less equals val, because the largest number less equals val will be this. M dot lower bound is giving you this. So it is basically the smallest number less equals val itself. Not really smallest number less equals val, but this is what is m dot lower bound, and this is what m dot upper bound returns. So you could name it. This is definitely the smallest which is greater than val, but this is something else. This is not the largest which is less equals val. This is not the smallest which is less equals val. This is basically the value which is as close to val as possible, and the first of such. What is the key here? So ordering is, so containers order. So I am just telling you that for maps or for any container which takes key value as input, the ordering is always on the basis of key. So for maps, you will not have this scenario ever that you will have three vals. You will have exactly one val because a key can always be unique, will always be unique. But for a multi-set or a multi-map, you can have this. Right? So I just told you the lower bound and upper bound generally on any container. If val is not present, then lower bound will be previous one. Yes, you're right. And if val is present, then it will be the first occurrence of that. Right? And upper bound will always give you one more than val, irrespective of whether val is present or not. Okay? Everyone understands lower bound and upper bound? So now tell me if you understand that. In this question, can we use a lower bound or upper bound on the prefix sums? Which one can we use, if we can use? Or can we use both? So how am I designing this now? Now let's come to the design of this map. So if I'm using a map or a set, what will be my key and value to be able to enable me to give solve this question? So let's see. So for a given j, you had to find the largest pi. So your searching will be on the basis of pi, right? So definitely your key will be pi, right? Do you understand this? Because your searching is on the basis of pi. You have to find the largest pi such that pi is less equals s minus k. Correct? So your searching is on the basis of pi. So your key is always that on which your searching is in the structure, in the data structure that you choose. Right? So your key will definitely be pi, the sums. But what do I have to find? I have to find the length of this array. So I do definitely need the index, right? So can I keep the value, the index as the value? Then, so that now my map will be keyed by the prefix sum and will have the index as the value. And in this map, I can use, I will use one of the two, either lower bound or upper bound, that you will tell me which one. But I can use one of these two to find one such pi, the largest pi, which is less equals s minus k. From there, I will get the I, and the length of the array will be j minus I plus 1. Right? And I will keep taking the minimum for all j. Correct? So this is how am I thinking. So my question to you, the only unsolved piece of this puzzle is this. Which one do I use to solve this question? I have all the PIs in the map. The question is, I have all the PIs in the map. For a given j, I have to find the largest pi, which is less equals s minus k. So which function can I use to find that pi? Lower bound? So lower bound will give me a pi which is less equals s minus k. So in this map, it will obviously be the scenario that you will have at most one s minus k, right? You cannot have more than one s minus k, right? So your lower bound will either be on this element or on this element, right? And your upper bound will always be on this element, correct? So you can use the lower bound exactly. The lower bound will give you the answer. Or you could use the upper bound and subtract by 1. That also will be fine, right? Because there is only one occurrence. I mean, in any case, you can use an upper bound and subtract by 1 also, right? So what I'm trying to say is, let's just giving you a heads up. If you have val, multiple occurrences of val, let's say you're using a multi-map or a multi-set, and then your upper bound will point here and your lower bound will point here. So then if you need this, you cannot use a lower bound. You will have to use an upper bound and subtract by 1. If you need this, then you will have to use a lower bound. You cannot use upper bound and subtract by 1. Right? So in this kind of a picture, this is how you choose. But because here you have exactly one occurrence of val because of the uniqueness, you can afford to use both lower bound and upper bound. Do you follow what I'm saying here? You can use a lower bound exactly, or you can use upper bound and subtract by 1. Did you understand?
Sir, in the lower example, if you need the middle one, what we will do?
You cannot find middle one with in log n just by lower bound and upper bound. You will have to traverse and keep a count then. So that worst case can be order n by 2 or order n basically. Yeah, n by 2 matlab at least. Okay.
Sir, is it upper minus 1 equal, does it tells the index?
It will give you the object that you insert in the map. So if you're inserting a key value, it will give you the key value. If you're inserting only a key, then it will give you the key. But the ordering is always on the basis of the key.
Okay, okay.
So everyone understands this? There is a slight, so you should understand this picture as well as this picture and why we are doing this picture here. For a multi-set, this will be the picture. So then you will have to decide wisely. Here, because it's a set, our choice really doesn't matter because there can be exactly one occurrence. So lower bound and upper bound will just be adjacent to each other in a single, in a map or in a set. But in a multi-map or in a multi-set, they can be spaced apart by more than one. So then the algorithm reduces to, basically I can just keep putting all the prefix sums one by one. As soon as I attempt my j, I can use, and I will insert all these on the map. In the map, the key will be the prefix sum and the value will be the index. I can keep inserting. When I am at a given j, I can find using m dot lower bound or m dot upper bound the appropriate I, do j minus I plus 1 and take a minimum. Okay, let's see the code quickly. We have spent a lot of time, I think. So this is the question. So let's see. I will use a map. So I'm just using m. I will need an I and n. So let's iterate. First things first, the prefix. To take care of the prefix, what is the prefix? Empty prefix array sum. Sum is 0, and what is the index? -1. So I'm just putting that. I think we have discussed on this quite a number of times why we do this. Now what I will do is So for this, I will need to keep a cumulative sum, which will be 0 to start with. So now I add it. I have a cumulative sum. Now I have to find s minus k, right? So this cumulative sum minus this s, right? So what will I do? And I have to do, let's try lower bound first. So lower bound will be as it is, correct? So I will do if m dot lower bound on s minus k. So s minus k is cumulative sum minus small s. So if this is not equals to m dot end, that means I found one. So let me store the lower bound in an iterator. So that I can reference it. So this is it. So if it is not equals to m dot end, that means I now have found one, correct? So I will have a global result, which will be int max to begin with. I can do keep taking maximum with. Now I will say this will be I minus it arrow second will give me the index, right? Plus 1. So I minus, so this is j minus I plus 1 I have done. I is j and it arrow second is I. So if I found it, then this is how I update the window. And then I will insert it. So I will insert in this with the index I. And finally, if my result is int max, so that means I didn't find any, then I will return 0, otherwise I will return result. This is minimum. So this will be cumulative sum. I have to insert the prefix sum, which is cumulative sum, not cumulative sum minus s. Where did this go wrong? Cumulative sum minus. Can anyone point out the mistake? In case of negative numbers, so map you can insert negative numbers also, right? Should be fine. That's not the issue here. Okay, sum is 4 here, right? This will not be 1. there will only be I minus j. This will be j minus I, right? Because I you are not including. When you are subtracting j minus I you are not including in the sub array, right? So this will be j minus I. Right? Did you understand the mistake? This will work mostly. Array. It will be j minus I only, right? Why will it be j minus I plus 1? No, that is fine. So are the numbers all positive? The numbers are all positive. So the cumulative sum will be strictly increasing, right? So you will not have two cumulative sums with the same index, right? So you can insert all of them. With some greater equals s. There's the mistake. So this subarray needs to be of some greater equals s. From there we said that s minus si. So si is less equals s minus k, which is what we are doing here. What is the case where it is failing? Cumulative sum I have initialized to 0, so I have not screwed that. This looks good to me. No, why it is screwing up? Anyone has any, can you spot the mistake? Any hunches as to what is going wrong here? The math was right? So I have to do the total sum as greater equals k, which basically means that sum is sj, right? That was basically s minus si. From here I can do it. This is s minus k only, right? And I have to find. So let's just see what lower bound does. pointing to the first element in the range which has a value not less than val. Okay, so it points to the first value greater equals val, lower bound, and the upper bound is basically then, okay. Yeah, so the definition of lower bound is wrong. What I told you is wrong. First element in the greater, yeah. So the picture is this then. I keep getting confused. So this is not the picture. The picture is, this is the lower bound, which is not less than, right? Which is not equal. It told, so let's say these are all equal to val. So lower bounds definitely, upper bound is definitely this. So it is the first which is greater. And lower bounds definition was, if you see, it is the first element which has a value not less than. So it is basically the first element with a value greater equals val. So in this case, this will be the picture. But even in that case, this should be fine, right? This will be the upper bound. And this will be the lower bound if it exists. So the mistake is if it does not exist. Yeah, so there is a mistake here, which, so lower bound will not work in this case. So I'll just tell you the definitions. So lower bound basically points to the first element which is greater equals val, and upper bound points to the first element which is greater than val. This is the definition of lower bound and upper bound. So now tell me, if this is the photo, this may or may not be present. Will lower bounds work? So lower bound will give you, in case this value is not present, lower bound will give you the position to the first index which is greater than val, right? But you have to find the last index which is less equals val, right? So if val is not present, then lower bound will not be correct. Do you see this? Others, like, do you see my mistake, what I did wrong in the definition of lower bound and upper bound, and what is the actual definition? Do you understand now? And do you see the mistake in the lower bounds? So then you could handle it in two ways. Once you get that element, you can either check whether it is equals to or not. If it is not equal to, it is strictly greater, then you can reduce by 1, right? That is one way you could do it. The other way you could do it is, which is always safe, is that you could take the upper bound and always subtract by 1, right? Then it is guaranteed, because upper bound is telling you that it is the first one which is greater than val. So you can always take the upper bound and just subtract by 1. It will be less equals val, right? And it will be the largest such. So this problem you can do with upper bound. We will do both then. Upper bound, so just take the upper bound and subtract by 1. If you want to do it by lower bound, then you will have to handle the cases. So if you do it by lower bound, if the element that you get is equals to the value, then you are good. If it is greater than the value, then you will have to subtract by 1. Right? Do you understand this? So let's try this then. Let's try both of them actually for learning. Yeah, so let's try lower bound itself. So if IT is not equals to m dot end, so that means you have found one. So you have two cases here, that if IT arrow first, if this is equal to the value that you're looking at, then you should just subtract it once. You are good. If it is greater, then you should just subtract it once. Correct? And then you can take the minimum. If it returns m dot end, then what does that mean? That means that every other element is less than cumulative sum minus s, right? So then the last is the answer. You will have to take care that it is not equals to m dot start. If it is equal to m dot start, then you cannot reduce. So if it is equal to m dot start and it is greater, then obviously you don't have a solution. So if it is greater and if it is not equal to m dot start, then you will do IT minus minus and take the result. Else, if it is equal to this value, then you will do this. Just very dumb way of writing the code. And if it is equals to m dot end, then basically means that everything is less than k. Everything is less than this cumulative sum minus s. So then the last one will be your answer, as large as possible. So you will do that. Now let's see. What is the syntax error? Begin. It will be begin. Okay, this is one way you could do it. If you want to avoid all these cases, then the safer way is doing upper bound. So you could just find the upper bound, and if it is not equals to m dot start, then you could simply subtract. So it gives you the first which is greater, right? So if the first element itself is the first which is greater, then you don't have a solution in that case. Otherwise, everywhere else you have a solution, which is basically you just reduce by 1 and do this. अरे फिर से start लिख दिया, begin. Is this clear now? Both the cases with both lower bound, upper bound, the approach, the view, everything? Can I have acknowledgements from whoever is left alive, following, saw the mistake, saw how we debugged it, like the mistake in understanding lower bound and upper bound? So you understand all this, right? Minus minus IT, begin, end. You are comfortable with that? All right. So this is then basically, we just took an example wherein we had to search and our searching needed some ordering, and we used a BST to search. Okay. There are more such questions. So that basically is, we can continue tomorrow more on this. So we will basically, we have questions on heaps that is left, and we have a couple of data structure design questions that are left. I will just paste the link to the questions, give it a try, and we will discuss them tomorrow. We will need to have one more class. I actually thought so even today that we will need one more class easily. Try all these questions. I will paste it on the Slack channel as well. Give it a try and see if you can try some of hash tables and 2 pointers questions also. We will cover a couple of them in the next class. We've done a lot of theory these days. So these questions, just try them. They are not links, so just copy them, and you can just copy and keep them and try them, and then tomorrow we will continue. Okay. One last thing is basically the debugging of the heap. So the problem there was that we were doing heap sort and then we were doing insert again. But when we were doing heap sort, we were removing elements, right? We were deleting them. So after doing heap sort, virtually the array is empty, right? So you cannot keep the same value of n and insert, like it will go haphazard. So what I have done is I have just removed the heap sort. So we are just doing the minimum and then inserting and then doing a heap sort. So we have this array, we are deleting 1, then getting the next minimum. So we should get 3 then. And after that, I am inserting 5 and then I'm printing everything. Okay, so let's just quickly see this in action. I haven't run it. I just got the idea that this is what we are, where we are making a mistake. So now if you see, the first minimum was 1. I removed it. So then the next minimum became 3. After that, I have inserted 5, which is, and then done a heap sort. So everything is working. 5, I am able to get in the right place. Okay. So I will share both these codes with you. So today we looked at a lot of implementation of BSTs as well as heaps. So you can take the BST file from me as well, and you can try it. I haven't run that. I didn't run it in front of you, but you can try running it. You can call insert many number of times with the numbers, with some numbers, then search with, and so you can try that. And I think it will work. If it doesn't work, then you can let me know and we can see where we have done a mistake. Okay, so I will share both the codes with you. We did an application wherein we saw that we needed to search, and the thing that we needed to search needed to have some ordering, and we used a BST for that ordering. In the process, I just defined what lower bounds and upper bounds are. And tomorrow we will look at more such problems on heaps in particular, and do DS design of LRU cache and LFU cache as well as median from data stream. Okay. All right, guys, then I think we are good today. Let's meet tomorrow again. I will paste the agenda of the class tomorrow in the group chat. And thank you for joining. I will see you guys tomorrow. Good night. I will just stay around for a couple of minutes if you guys have any questions. Otherwise, we can end the meeting.
Sir, could
Yeah.
you go back to the previous question? Like why I minus j is there in while storing results? Results comma I minus the it2 second is there, right?
1 second. I'll just open it. Yeah, it is I minus. You don't understand why it is I minus I, right?
No, why it is I minus j
because the subarray that you are considering is from I plus 1 to j, right? So what is the sum of that? What is that subarray's length from I plus 1 to j? If the indices are j and I, it is j minus I, right?
Okay.
So we have taken that. It arrow second is the index and I is the current index. So I is j actually here, right? And it arrow second is I, if we are taking the same example.
Okay. So can we can use it both way?
Use it both ways.
I mean, you said right now we can use j minus I, right?
We are doing
The
j
length.
minus I only. Why are you going with the name? I is.
Okay, I is that
I
the
is the
index.
examples j, the theory.
Okay, okay, okay.
And it arrow second is the theories I.
Got it.
The names I have not taken the same. That may be the reason why you're getting confused. Okay. Any more questions? All right. Okay, guys. Cool then. I will see you tomorrow. Thank you. Good night.